Bismillahirrahmanirrahim. Welcome to Easy Learn. We are discussing in the previous episode Newman's equation that is basically related to Faraday's law. Actually, it is a Faraday's law basically, and the combination of Faraday's law and Lenz's law. In this video, we are going to discuss the Faraday's law only and very precisely. So let's start the discussion from the name Faraday's. Basically, the Faraday scientist you will see here in this diagram, in this picture, that this is a picture of the Faraday scientist. It is named after the scientist Faraday, Faraday's law in 1893. So the coupling between the electric and magnetic field is based on an experiment. Basically, the Faraday wants to show one thing, that he just showed that there is a relation between the magnet. For example, this is a magnet and north-south pole of the magnet, and these are the magnetic field lines. This is the magnetic field. And this is magnetic field, while this is a current carrying conductor. If we just connect it with a source, it is a current carrying conductor, and this is the, for example, direction of the current according to the conventional current flow. I is from positive towards negative, and there is an electric field in a when the current is started to flowing through the conductor, and the direction of the current carrying conductor which carries the electric field is the same, that is the direction of the current. So it shows that there is a relation between this magnetic field and the electric field, means current and magnetic fields. So what is the relation that is explained by Faraday? Is based on the experimental relation. He is performing so many experiments, and finally he succeeded and showed up this, and this is very useful assumption. We are going to use it in very experiments, although nowadays our motors are very much changed and modern style, but they are based on this principle, the relation first discovered by his. That's the why the honor this is named after the Faraday's law. He's received the prize also, and also the unit of the capacitance is named honor of the Faraday. That is, the unit of the capacitance is farad. That is named after this scientist. This was actually the model that he used to explain this theory. That is in 1831, in August 1831. This law was formulated in 1831 by the Michael Faraday after the series of experiment. Faraday's disc. This is called Faraday's disc. This disc is made up of aluminium, and it can be rotated. This is a fixed axis. This is a handle. We can use it to rotate, and from this handle that is in the center, this handle, there is a wire that is connected internally, and coming from here to this contact that is called B. This contact is 1. This will be one contact because we need two contacts, positive, negative, in this case for the use it as a current. Second contact is here, that is named as a B dash. It takes current, or its connection is basically through this, and here by using the two bolts we provide a tension to the a thin metallic bar or metallic just chip, which is just connected to, its pressure is inside, and it is due to the pressure of this tightly bolted here. It is just always connected with the rotating disc, and its connection is, when it is rotated, it is still connected due to the pressure is inside. So sliding contact here basically. So the other one connection is B dash, and we will try to use it, and our connection will be like this. Here is the galvanometer, very sensitive galvanometer, works in both direction, either movement is this, and if we rotate it against this, our rotation is changed, definitely the direction of the current will also be changed. And the second thing on the board he fixed this one to provide a strong magnetic field by horseshoe magnet. This is a horseshoe permanent magnet. Metallic disc is inside this magnet. This is the front view, side view, sorry. uh, this is suppose a disc, and it is the center, and disc is rotating. Okay, so this is a magnetic field lines. These are the magnetic field lines. When disk is rotating, basically it is cutting here from here magnetic field lines. So change in magnetic field lines in the disk means that this is, consider this as a loop. Okay, disk as a loop, and this is the magnetic field, and when it is rotating, it is actually cutting the magnetic field lines. It is passing through change in magnetic field scenario occurs. So another view of this is just like that. Maybe you can understand well from this diagram. This is a north and south pole. For the demonstration of the Faraday's law, it is actually the side sliding contact, that is B dash, I want to show you here, and it is connected with sensitive galvanometer. The internal connection can be obtained from the inside pivot point where it is rotating the rotational axis. This inside point is taken from the actually from the rotational point, where actually, when you know, the in the previous diagram I wanted to show you that, for example, this is a conductor placed in the magnetic field. When the magnetic field lines are changing, the changing magnetic field, holes are moving towards the one end, lining up, while the electrons are coming to the other point. And due to this, what happens due to this, actually this will be behaving as a majority in the negative charges, and it will behave as a negative, while this will as a positive. Here the magnetic field lines are going to align up, and the electric due to which the charges are moving in the opposite direction, and here this will behave as inside there, this will behave as a one terminal, while the outside of this will be the second charge majority. So we will be going to use, when rotating this, the current, it shows the deflection by the galvanometer. So this was the basic principle. This is the definition that for example, this is our permanent magnet north south, and this is a current this is, sorry, a simple loop that is a closed loop. Remember that it is connected with the galvanometer to make sure that if the current or any scenario of the current can be is there, presence of the current can be displayed with the galvanometer here. Actually, when it is bring closer to the in the jurisdiction, this is, remember that this is must be in the range, not so far that you are changing the magnet on from the other room and the loop is available here. Make sure that the loop is closer to the magnet, and it is in the range. If there is a ferromagnetic material here, small piece, it may feel the attraction or the repulsion force. Attraction usually unmagnetized in the condition. So if you are going to change the velocity of the magnet either in this way or this way, he noticed that the deflection, Faraday observed that if he move the closed loop in the magnetic field of a magnet, or if he just move the magnet while the loop remains stationary, this is the second case, he is changing the loop while this time the magnet is stationary. In the both cases, he noticed that the direction of the current is basically noted due to the galvanometer. The deflection is noted, recorded on the galvanometer. So it means that also it shows Faraday claimed that the current was not due to this external sources, means due to wireless transfer of the electric current into the loop. No, this is not the wireless transmission. It is actually induced in the loop due to the change in magnetic flux, that is the flux. And by changing the flux by magnetic field lines, or you can just change the loop, anything but changing in flux, magnetic flux is the only thing you need to do. By this you can you can receive your charges alignment like current is produced in the coil. He found that the current was proportional to the rate of the change of flux. As the current is due to the induced voltage in the loop, so this is called electromotive force, the induced voltage. Electromotive force, EMF, is the induced voltage. It's not as volt, it is actually voltage. So electricity means that is produced is called, for example, this is voltage, or that is produced voltage, induced EMF, or electromotive force simples. In the previous episode we discussed the Newton's equation, that is the same. Actually we just saw the Newton's equation with delta phi divided by delta t, that is actually same. Delta represents the change in previous diagram, previous episode with here also. If the b, I in earlier episode mentioned that you can also write the b, it doesn't matters if you write or just hide it, because phi is always used to represent the magnetic flux, and it is understood. If you write b, it's good, you can write it in the subscriptions, but if you don't, then it's also understood. D over dt, it is basically representing the change with respect to time. D over d, it shows the derivation. Actually derivation is the change, so is the same, no issues. You can also write in this way. Negative represents the direction, it is opposite in direction. For example, your actual magnetic field is from due to the permanent magnet is from left to right. The induced it always trying to oppose to the applied magnetic field, and if the n here, and I can write it here n also in this formula. If I have more than one loop, I can write it here. If I have one loop, then it is, this formula can be used, means one. If we do not write one loop, one multiplied by this term, it will be still this term, so we cannot write here. But if we have more loops, for the maximum obtain of the maximum, if we want to gain the more magnetic and catch up the more magnetic field lines, it means that we need more loops or the strong magnetic field, so we can write here n to use it later on purposes. Electric basically current in the generators, large generators. This generator, you will see, it can produce the 7 amperes of the current, sorry, 9 amperes also, I think, if I remember. If I'm wrong, if I'm correct, it can produce 9 amperes and 7 volts, I think. So basically I just want to show you here that electric generator uses this principle to generate electric current nowadays. So Faraday's law is very important. Coming up next is the Lenz's law, and we will try to discuss the Lenz's law in the same pattern as we discussed the Faraday's law, precisely because this is the introduction to electronics, and when we are going to discuss another series, we will discuss all the things in details pattern. So stay tuned, watch, learn, grow.